All right, thanks. I'll begin. Heavenly Father, we thank you for this day. Thank you for the students. Just pray you'd bless our time together. Just help us to understand Taylor's theorem today, Lord. In your name I pray. Amen. I'll spare you the quiz today, if that's all right. Don't worry, I'll bring back one soon. Don't get the wrong idea. There's a reason I couldn't do anything yesterday. I was getting sick, and now I'm sick, so I should be at my new normal. I have lowered expectations for what I can calculate today. We should be okay. All right. So what I'm going to try to do here is to introduce you to the notion of a Taylor series. This will culminate in the statement of Taylor's theorem. But to start with, let's just talk about, the so-called Taylor polynomials. All right. So here's the problem. We're given a function, say f of x, and we wish to find a polynomial approximation to f of x near x equals to a. All right. So let me draw a picture of what we're trying to do. All right, so let's put the function itself in black. All right, so maybe the function looks like that. I don't know. So here's y equals f of x. I'll put it in black. So if you want to approximate the function with polynomials centered at a, you start out kind of, start out the most kind of boring thing you can do. It's almost too boring to even mention, but it's this. It's just y equals to a constant, right? So if we have y equals to a constant, what's that constant going to be if it goes through this point in the graph, which is what? That point is a comma f of a, right? So that means y equals to f of a. All right? This is very silly, but this is the zeroth Taylor polynomial of f centered at a. All right, what's the next thing you can do? You want to do a little bit better, although my point, poor choice. Let me make it a little bit more interesting. Make it a little bit more interesting. If I do like this, there, it's more fun. What's the next thing you could do? How about this? That was supposed to be a straight line. This here, right, would be y equals to a line, right? That's the tangent line if I had drawn it better. And what's the formula for the tangent line through the graph at a comma f of a? You do what? You do f of a plus f prime of a times x minus a. Perhaps you recall that, right? Right? And this we know from Calculus 1. So that gives us a pretty good approximation to the function close enough to the point of tangency, right? Well, what's beyond this, right? What's beyond the, this is, again, you might call this t sub 0. This you could call t sub 1 of x. Maybe there should be an a on that because the center is a. If we choose a different center, we get different Taylor polynomials. What would the next thing be? the best quadratic approximation to it, right? If I was to be so foolish, so I'm still, my graph is too yucky in here. I wanted it to be more like, I'll fix it in just a second here. Sorry. So my point was, you know, if you look at this, you can see the green line is only close to the graph, you know, a little bit close. If I'd drawn this better, you'd see the blue line lines up with it a little bit further. The quadratic approximation would be more like you just kind of fit a parabola, right? You fit a parabola in here like this, something like this. This would be T2 of x, all right? Now, we don't know what T2 of x looks like, all right? All we know at the moment is that T2 of x is equal to some constant, let's say C naught, plus some other constant, let's say C1 times x minus a, plus C2 times x minus a squared. Well, I mean, I guess you're saying, well, well, I mean, if you don't like that, if you don't find this natural, I suppose I could start with, you know, a plus bx plus cx squared, vice versa. But this is much easier to think about. And that like naturally continues the story here. Like I've already seen that the first Taylor polynomial has the form like a constant plus a number times x minus a. So like continuing this pattern, I want to expect some constant times x minus a squared. So what do these constants have to be? If there is such a polynomial approximation to f, right? If this is approximately f of x for x near a, then what should we base that nearness on? Well, how about this? We want T2 of a to be equal to f of a, right? We want T2 prime of a to be equal to f prime of a, right? And what else do we want? Because geometrically, what does the prime do? Like the first derivative matches the slope at the point of tangency, right? To make the second derivative match the function, that would be matching up the concavity at the point, right? So a natural thing to try would be this, T2 prime prime of a equals to f prime prime of a. So these are conditions we want this Taylor polynomial to meet. What happens when you plug in a into this? 0, right? 0. We get what? We get C0 equals to what? F of a. Well, that wasn't too bad. We got C0. How about when you differentiate? What happens when you differentiate T2? Let me write it off to the side here. dt2 dx is equal to what? It's equal to the constant differentiates away, then I get x minus a plus 2 times x minus a. Oops. I forgot my C1. I get C1 plus C2. Oh, goodness gracious. I warned you guys, I'm sick. All right, 2C2, I'll try. But you'll have to correct me when I make mistakes today. I guess it's like any other day. All right, so now if you plug in x equals to a, what happens there? T2 prime of a is just what? C1, right? So C1 is equal to f prime of a. All right, let me put a little side calculation here. What's d squared T2 dx squared equal to? Just 2C2, right? So plugging in x equals to a is kind of a non-event here. 2C2 is equal to f prime prime of a, right? So what's that tell us? C2 is 1/2 f prime prime of a, right? So in total, what did we just figure out? We figured out that T2 of x the best quadratic approximation to the function at the point of tangency A is going to be given to us by f of a plus f prime of a times x minus a plus 1/2, right? 1/2 f prime prime of a times x minus a quantity squared. All right, that's T2 right there. Does this make sense? You see where the half came from? What happens if I try to find the best cubic approximation to this thing? I'm not sure exactly, but it's probably something like, I'm out of colors. I need another color. Do I got a color? Oh, man. Oh, well. Maybe I got another color. Let me see. Nope. I guess I'm going to go back to green again, but it'll be clear enough. Look, the cubic would be something like that, all right? And this would be what we would call y equals to T3 of x, right? Now T3 of x would have the generic form C0 plus C1x minus a plus C2x minus a squared plus C3x minus a cubed. The best cubic approximation to the function there. Now, almost the same calculation as we just did shows me what? This is equal to f of a plus f prime of a times x minus a plus 1/2 f prime prime of a times x minus a squared, and then plus, let's work this next term out, right? So what is the third derivative? Excuse me. Well, first of all, what's the first derivative? T3 prime. T3 prime of x is what? C1 plus 2 C2x minus a plus 3 C3 x minus a squared. What's T3 prime prime? We got 2C2 plus 6C3 x minus a, right? What is the third derivative then? T3 prime 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 of x is what? 6C3, right? And we want that to be equal to f prime 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 of a. Right, so my third coefficient then is going to be, I'll put it over here, 1/6 f prime 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 of a times x minus a cubed. So you see how these are working? What's the structure here? Let me generalize a bit. Here's a definition for you based on this calculation we've done. Given smooth f of x near a, we generate the kth Taylor polynomial centered at a as follows. F of, t, I'll say t sub k of x is equal to the sum. K equals 0, well, tell you what, let me put the sum, I'll put the sum for, I'll do the part you'll understand better first. All right, so f of a plus f prime of a times x minus a plus 1/2 f prime prime of a times x minus a squared plus 1/3 factorial f prime prime of a x minus a cubed plus dot 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 plus 1/k factorial. The kth fold derivative of f evaluated at a times x minus a to the power k. So the point here is that this is really the zeroth derivative at a over 0 factorial. 0 factorial 1, the quote-unquote zeroth derivative of the function is just the function. This is our convention, okay? This guy right here, what's this? This is the first derivative evaluated at a over 1 factorial, also known as 1, right? If you look at, not the whole thing, just the coefficient. Excuse me. Oh, goodness gracious. Sorry. This is the second derivative at a over 2 factorial. Of course, this I've already written as the third derivative at a over 3 factorial. And then finally, the kth derivative of the function evaluated at a over k factorial. That's the pattern. So we can write this much more efficiently in the summation notation simply as follows. Tk of x equals to the sum, all right, k equals, oh, I'm sorry, n equals 0 to k of the nth derivative evaluated at a over n factorial times x minus a to the power n. This is the nice formula for the kth Taylor polynomial of the function. Yep.
Where did the 2 factorial, what happened with that?
2 is 2 factorial.
Okay.
So 0 factorial is 1, 1 factorial is 1, 2 is 2 factorial, 2 times 1, which is 2, 3 factorial is 6, 4 factorial 24, 5 factorial is 120. Oh, we went over this yesterday. Any questions about this so far? So we can calculate Taylor polynomials for functions that you know and love, or just know, or just functions. I don't know. Let's not be. So for example, you know, I could take a equals to 0, f of x equals the sine of x. So f of x sine x, f of 0, f prime of x cosine x, f prime prime of x minus sine x, f third derivative of x minus cosine x, f fourth derivative of x sine x, f fifth derivative of x cosine x, f sixth derivative of x minus sine x, f seventh derivative of x, like, is he ever going to stop? I'll stop. Cosine x. I'm going to stop there. All right, enough already. Of course, this repeats over and over and over again, you know. Evaluate these functions, evaluate these, rather, derivatives of the sine function at 0. What do you get? F of 0, 0. F prime of 0, 1. F prime prime of 0, 0. F prime 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 of 0, minus 1. F the fourth derivative at 0, 0. F the fifth derivative at 0, 1. The sixth derivative of f, 0. The seventh derivative evaluated at 0, minus 1. So with this data, I can calculate the 7th Taylor polynomial of the sine function. So T7 of x is going to be equal to, so we do x minus 1 over 3 factorial, x cubed, plus 1 over 5 factorial, x to the 5th, minus 1 over 7 factorial, x to the 7th. And there you go. That is the 7th Taylor polynomial of the sine function. It's a pretty good approximation to sine. If you don't have a calculator which does sine, you can use this Taylor polynomial to get a pretty good approximation to the sign of whatever you like, as long as it's relatively close to the 0. Like the approximation of the Taylor polynomial to the function is optimal when you're close to the point at which you're centering it, right? I mean, it's dead on at the point, isn't it? Let me show you another example, and then I'm going to project some things. I got some pictures in my notes that I got to share with you because they're far more beautiful than anything I can draw on this board. Any questions about notation or anything here for long? All right. So for example, we could have f of x equal to x cubed. Find T3 of x where with center A equal to 1. Okay, so f prime of x is what? 3x squared. F prime prime of x equals to what? 6x. What's f prime 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 of x? 6. All right, so this gives me so of course f of 1, 1, f prime of 1, 3, f prime prime of 1, 6, f prime 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 of 1, 6. All right. Thus, T3 of x is what? 1 plus 3x plus 6 over 2. Oh, I'm an idiot. I can't follow my own rules. It's right here. I mean, right here if you prefer. I've erased the next relevant term. I better erase that since it's only half true. Oh well. I wish I hadn't erased that. It's too late. What's done is done. Okay, so here it is. I'll write it symbolically here. So what we're looking at is f of 1 plus f prime of 1 times x minus 1 plus 1 half f prime prime of 1 times x minus 1 squared plus 1 over 6 f prime 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 of 1 times x minus 1 cubed. That's T3, centered at 1. Now I'm just going to plug in the numbers 1, 3, 6, and 6. What does that give me? One plus 3 times x minus 1 plus, let's see here, f prime prime was 6. 6 over 2 is 3, right? And then 6 over 6, just 1 again, right? So there you have it. This is the third Taylor polynomial of the function. What's the fourth Taylor polynomial here? Right, T4 of x is just equal to T3 of x. In fact, Tn of x is equal to T3 of x, which is, by the way, equal to f of x itself for n greater than or equal to 3. Maybe I should use a k there. I should probably use a... I know sometimes I'm going to use a k, sometimes I'm going to use an n. I hope you guys can not be confused by that. But I'll put k in both spots just to be a... That's how I've been using k here in this lecture up till now. Okay, so the point is, it may not be obvious to you, right? Is it obvious to you that that's equal to x cubed? Here's a way I would derive it. If I had f of x equals to x cubed, one way I could get to the center One way I could recenter this at 1 would be to subtract 1 and add 1 and cube it, right? So this is really just x minus 1 plus 1 quantity cubed. If I think of this as a, and if I think of this as b, then the binomial theorem gives me a cubed plus 3a squared b plus 6ab squared, no, plus 3ab squared plus b cubed. No, I'm not got that right yet. Second here. ab squared plus, there's a 6 in here, isn't there? Just a second. 1, 1, 1, 1, 1, 2, 1, 3, 3. Oh, it is 2 3s. I'm an idiot. So 3ab squared plus b cubed. That's how to multiply out a cube. But that is x minus 1 cubed plus thrice x minus 1 squared plus thrice x minus 1 plus 1, which is what we got over there. So you can see by direct algebra that what we just produced with this Taylor polynomial is in fact the same. I mean, they're equal. Let me put this into words. The best polynomial approximation to a polynomial is the polynomial itself, which is kind of dumb. But of course the formula looks different when we recenter it at 1, right? So, any questions about this? So finding Taylor approximations to polynomials is not especially exciting. I think this is much more interesting. Let's take it to the next level. What's a Taylor series? Taylor series, what that's going to be is the sum n equals 0 to infinity of f n of a over n factorial times x minus a to the n. So if instead of truncating, the polynomial at order k, if you let that k go to infinity, if you just keep going and going and going and going, then you have what's called a Taylor series. This is the Taylor series generated by f at a. It's a somewhat delicate question to answer whether or not this, but in fact it's true. Given the right conditions, this will actually be equal to f of x near a. I'll put a little sometimes here. One of our goals at the moment is to describe when it is sometimes. The answer is, for functions that you care about in applications, it usually works right up until you get to an asymptote or something. It's relatively hard to find functions which don't have nice Taylor series, in the sense that they model the function. Any misbehavior on the part of the function will also be found in the series. So if the function has a vertical asymptote or something, then the series will suffer the same fate. All right? But there are other things which are more mysterious. Fun. All right, I'm working on it. Come on. Come on. You can go. Go in there. All right. So our ultimate goal in the next couple weeks is really to master how to calculate with Taylor series, how they're applied, what they mean, how to interpret them, and how to find them for functions. One way to find them for functions is just by the direct calculation like I've been showing you. But, all right. I mean, even for that sine function, that was kind of a pain, wasn't it? So we're going to build up a dictionary of standard examples we can build other ones from. Of course, at some point soon, we're going to have to stop and we're going to have to pay our dues, and I'm going to have to explain to you how we decide the convergence or divergence of this, right? Because that's a series, right? But this is an example of what's called a power series. A power series is a function which is defined pointwise by a series of power functions. So we should talk about that sort of more systematically. But before I get into that technical stuff, I just want to show you the big idea of what we're doing, which is what I'm working on right now. Okay. Anyway, so here we just went through this, right? I'm deriving that this is the form of the first Taylor polynomial and so forth. So we already went through this today. All right. Here I use a j instead of an n, but it's the same thing, right? All right. How about the exponential? What's the exponentials? So I decided to show you how to find the Taylor's polynomials for the exponential. Again, the difference between Taylor polynomial and Taylor series is Taylor polynomial stops at finite order, whereas Taylor series is without end. All right. So here we go. You know how to differentiate the exponential. We can do it all day long, right? Like, what's the 334th derivative of the exponential? What? E to the x. Very good. So this we can do. So of course, when you plug in -1, you always get 1 over e for the coefficient, for the whatever derivative of the exponential evaluated at -1, always 1 over e. So here's the zeroth Taylor polynomial, the first Taylor polynomial. The graph of this you've studied in detail last semester. That is the tangent line to the exponential at -1, right? This you understand. Here is the best quadratic approximation to the exponential centered at -1. Here's the best cubic approximation to the exponential centered at -1. And here's some graphs, a little bit better than the one I was creating a second ago. So what you're looking at here, the red dotted thing is the exponential. This is, of course, the tangent line. The green is the best quadratic approximation, and then you can see the best cubic approximation right here. As we go higher in order, the higher and higher order you go, typically, the closer and closer you stick to the actual graph, right? By the way, at any point here, we can kind of stop and smell the roses. Do you guys remember the second derivative test? Want to think about the second derivative? Let's take a second to think about the second derivative test. What would the second derivative test say? Do you guys remember? It says what? If f prime of a is equal to 0, then we can characterize the critical point a comma f of a as minimum or maximum locally via the sign of f prime prime of a, right? And to think about it. So basically, the theorem I'm going to show you at the end of class today, Taylor's theorem, says that so here's like the critical point. The critical point is where what? The first derivative is 0, right? So here we have y is approximately f of a plus 1/2 f prime prime of a times x minus a quantity squared. And you know what? We also have that here. But what's the difference? One is like, basically, it's what it's saying is locally, right? So here we have locally the function's like a, oh man, come on. Contrast of white on white. Let's see here, let's try that again. There we go. Doofus. Let's see here, me, not you. So that's more exciting. As you can see, this would be this is like, t2 of x. Here's y equals t2 of x. The next thing, the cubic term, is like x minus a cubed times the third derivative, right? The next term that I'm neglecting is like x minus a cubed. X minus a cubed is super small close to the critical point. Comparatively, x minus a squared is ginormous, which means x minus a squared wins, and the local behavior of the function is totally dictated by the second derivative. If the second derivative is positive, it's a minimum, because it's like a quadratic that opens up local to the graph. If second derivative is negative, it's like a quadratic that opens down. And that's where the second derivative test comes from. It's simple as that, right? I'll make that a little bit more rigorous with the theorem I show you at the end of class here. But all right, any questions about this? Or you can understand things we did before in more depth with this theorem, this technology, if you will. Here's another example. I think I'll last another 10 minutes, but we'll try. So here's the first few Taylor polynomials centered where? At 1 for this function. F of x equals to 1 over, where did I put my laser? Oh, thank you. I wouldn't have found that for a while. You're a good person. Some people would just like not tell me just to see how long it took me to find it. So it's good. It's good. So you can differentiate this thing. Oh, well, it's not too bad. You differentiate and differentiate and differentiate and differentiate, right? And if you plug in 1 to this, you get what? You get 0 for this, because you get 1. You get minus 1, plus 1, 0. F prime of 1 is what? Minus 1 over minus 1 squared, so it's minus 1. F prime prime of 1, if you plug in 1, you get 2 over minus 1 cubed, so it's minus 2. The third derivative evaluated at 1 is minus 6. All right, so you plug in the point we're trying to find the approximation, as I say here. And so here's what I just said: 0, minus 1, minus 2, minus 6. So here's the first Taylor polynomial, the second Taylor polynomial, the third Taylor polynomial for this function. All right, that's what they look like. These notes are posted in course content in case you didn't know, right? This is my lecture notes that I on occasion use. And this seems like a good occasion. So in red is the function we're approximating with the Taylor polynomials, right? It's got a vertical asymptote at 1, all right? And basically, when I said that I mean, these Taylor polynomials, what's the domain of T3 of x? I mean, technically, all reals, all right? It will keep making, I mean, as a function, a standalone function, this will make sense for all reals. But the thing is, this Taylor series will stop converging to f of x as you go past this vertical asymptote. Like, you see as you go higher and higher here, like this is the third Taylor polynomial, right? This purple one. It's getting drawn closer and closer to the function, right? And as you go to infinity, it'll actually match the function, but it will not reproduce the function over here because there's this vertical asymptote it can't get past. This is my intuition for that. But anyway, there's an example.
So if you centered it at a
different point, like 3, it would look like this. Yes, very good question. Yes, so if I center it instead at 3, I would get a different Taylor polynomial, which I have same derivatives, just evaluated at a different point, right? Evaluating at different points will generate different coefficients, 2, 1. Well, anyway, it generates, and so here's what the Taylor polynomial centered at 3 look like. Again, of course, the T3 is closest, the longest, and the tangent line is the sloppiest amongst these. But, I mean, there's another example. Here's sine. I calculated this by hand for you. So here's a picture of it. What we're looking at, here's the actual sine function, all right? The red dotted. The fifth Taylor polynomial is the purple graph. So the fifth Taylor polynomial will actually get you out to about, let's see here, guys. This is minus 90 degrees right here. This is plus 90 degrees. So it looks like the purple guy gets you really, really close, out to about 100 degrees, plus or minus, you know? And then if you track the yellow one, which is what? That's the next one. So that would be T7. That's actually this thing, the one we calculated. That yellow one, it looks to me like it basically tracks sine a whole period. That'll go plus or minus 180 degrees to a pretty good approximate. I mean, it looks like to within a percent at least. So if you use this for the sine between minus 180 and 180, well, you better use radians. But for radians anyway, between plus or minus pi, the yellow graph is pretty well. I mean, it's even a little bit past, right? It starts to go off sine significantly when we get to here, right? I don't know. It's hard to see the yellow. And then what's the what's this? What do I have here? Is yellow the last one? Maybe. Wait a minute. Yellow may not be T7. Maybe. Oh, I think T7 might be the. Wait a minute. Which one's green? Oh, green is T3. Which is this one? Oh, this must be T7. I'm sorry. This is T7. But my comments are just about right. T7 goes to like here, then it starts dropping off. This yellow one that goes a little bit further must be the T9. Anyway, if you keep adding terms, what happens is you track the sine function further and further and further and further out. You can, yeah, it'll keep, I mean, basically if you have a nth order polynomial, how many turning points can it have? Quadratic polynomial has how many turning points maximally? 1. Cubic, how many maximal turning points? 2, right? So it's always, if you think about it, differentiate a polynomial, set it equal to 0. That's an n minus 1 order polynomial equation. It has at most n minus 1 solutions, at most n minus 1 critical points. So if you think about sine, right, you're going to need higher and higher order polynomials to make it track further and further out because you get more and more turning points, And it's not enough to have, I mean, anyway, I have not studied carefully to see how fast, it goes out. I'm not sure. I could make it more precise. Here's another one. The relativistic energy of a free particle of rest mass m naught is a function of its velocity v according to this formula. This is the relativistic energy. V is the speed of the particle, c is speed of light. You differentiate this thing, you get that, you differentiate it again. Anyway, long story short, here is the fourth Taylor polynomial to the relativistic energy. The zeroth term has physical significance. This is m naught c squared. It's the thing Trump would tell you Hillary's not very good at defending. This is the classical kinetic energy, which you know and possibly love from physics, or you dread it. I don't know. I like kinetic energy. Those problems are easy. You're working on them. But you notice this comes before that. This is way, way huger. I mean, it's more bigly in terms of energy than that. And then you've got this term, which is basically, the next term path is something like it describes the error in these two. Anyway, so here's a picture of that. Excuse me. Here we have the classical kinetic energy is in green, the relativistic kinetic energy is in red, and here's your cosmic speed limits given to you by relativity. But anyway. So, power series are important. These Taylor polynomials are important for interpreting physics. We understand new physics and old physics in terms of their interrelation is often given to us in terms of a power series approximation. It's more than just math and approximating functions. There's also physical stuff. So here's the theorem I was mentioning. This is Taylor's theorem with Lagrange's form of the remainder. It says that if you have k derivatives, this is basically a generalization of the mean value theorem, all right? Which says that if you look at a function which is differentiable and continuous on a closed interval, that there's some point in that interval where the average rate of change is equal to the instantaneous rate of change. That turns out is tantamount to saying that you can replace a function with its tangent line, approximately. And, well, anyway, I'm being a little bit heuristic there, but here's the theorem. F of b is the kth Taylor polynomial of b plus this remainder term of b. This is just the formula for the kth Taylor polynomial as we've discussed today. I'm evaluating it at b. And the theorem is not just this, it's that this remainder term is manageable in the following sense. There exists some c between a and b. So what this notation means is like the interval is either AB or BA. I just don't want to commit to B being before A or vice versa. So if you want it to be more less confusing to students, you could just say I'm going to prove it for A comma B, and then the proof for B comma A is similar. All right, but I was not thinking in this way when I wrote these notes. So
What's the symbol for I?
boundary. Yeah, well, it's the partial. Anyway, annoying notation aside, the remainder term, the error basically, is encapsulated by the k plus 1th derivative evaluated at c over k plus 1 factorial times b minus a to the k plus 1. What this is saying is that this polynomial is basically as good as the next term you're not using, evaluated at some point in the interval of consideration. And so, excuse me, I will just show you here. I'll get this out of what sorry. While I got this out, I got to show you something. We'll look at the proof some other day, okay, guys? But just to show you how the proof works, like here's an example. I've got this function, this red function, right? And I can calculate the Taylor approximation to it like that, right? I apply Lagrange's theorem. It tells me if I can bound. So this is what? This is the t2. So I look at t3. I look at the third derivative. I find a bound on the third derivative. And basically, however big the bound is, plus the width of the interval considered, will give me a maximum departure of the function in the second Taylor polynomial. Like it gives me an error between the function and the second Taylor polynomial. Lagrange's theorem tells me precisely how close the Taylor polynomial is to the function, actually, when used properly like this. And this is pretty greedy, but so I calculated the error bound from Lagrange's theorem, and like you can see that the function tracks this, the Taylor approximation is the green graph, and the real function's the red one. And here's a blow up of just this region. And you can see this gray bar, what this is the error which is allowed for in terms of the remainder in Taylor in the Lagrange's theorem. And you can see that my bound is by far no means is not sharp. I mean, it's definitely it's fitting it much better than my rather greedy error. And well, we'll look at this again another day. I know we're about out of time here, but I did the same for, if you look at this, here's the sine function, and I use the cubic approximation to the sine function, and I study, like, here's the error that I derived from Lagrange's form of the remainder, and here's how close it is. And anyway, we'll sort through this more some other day. I'll shut up. Thanks, guys.